The National Electrical Code, or NEC, mandates that the wire gauge used in an electrical panel must have an ampacity equal to or greater than the rating of the circuit breaker protecting that circuit. The rationale behind this requirement is to ensure electrical safety. The wire gauge dictates the maximum current the wire can safely carry. The circuit breaker is designed to trip, interrupting the circuit if the current exceeds its rated capacity. If the wire gauge is smaller than the circuit breaker's rating, the wire could overheat due to excessive current flow. This overheating presents a significant fire hazard. In the described scenario, 12 American wire gauge, or OLG, wire was used for the majority of the circuit, but a transition was made to 14 AWG wire for a portion of the run in the bathroom. This means that the section of the circuit using 14 AWG wire has a lower ampacity than the 12 AWG wire used elsewhere and also potentially less than the breaker protects it. Therefore, the inspector is correct in requiring that the wire gauge at the panel be changed to match the smallest wire gauge used in the circuit, in this case 14 AWG, unless the breaker size is changed to match the 14 AWG ampacity. The NEC does allow for the use of different wire gauges within a single circuit. However, this is permissible only if the circuit breaker rating is adjusted to match the ampacity of the smallest wire gauge used in that circuit. For example, 12 AWG wire could be used for most of a circuit, and a short run of 14 AWG wire could be incorporated, but the circuit breaker would need to be downsized to a 15 amp breaker, appropriate for the 14 AWG wire, instead of a 20 amp breaker. Understanding ampacity is key. Ampacity refers to the current carrying capacity of a conductor, typically measured in amps. It's the maximum amount of electrical current a conductor can carry continuously under specified conditions without exceeding its temperature rating. Several factors affect ampacity. Firstly, the wire gauge is critical. Larger wire gauges have lower resistance and thus higher ampacities. Secondly, the insulation type impacts ampacity. Different insulation materials have different temperature ratings. Thirdly, the ambient temperature around the conductor affects its ability to dissipate heat. Higher ambient temperatures reduce ampacity. Fourthly, the number of conductors bundled together in a raceway or cable affects ampacity. When multiple current-carrying conductors are bundled together, their individual ampacities must be derivated to account for the increased heat generated. When selecting conductors for electrical circuits, it's essential to consult ampacity tables provided in the NEC. These tables list the allowable ampacities for various wire gauges, insulation types, and installation conditions. Always choose a conductor with an ampacity rating that is equal to or greater than the circuit's overcurrent protection device, such as a circuit breaker or fuse. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance, which is the opposition to the flow of alternating current. It is typically expressed as a percentage of the source voltage. Excessive voltage drop can cause various problems. It can lead to inefficient operation of electrical equipment. Devices may not receive the required voltage to operate at their rated performance levels, resulting in reduced output, increased energy consumption, and premature equipment failure. Voltage drop can also cause overheating of conductors and equipment. When voltage drops, the current increases to deliver the same amount of power. This increased current can cause conductors and equipment to overheat, potentially leading to insulation breakdown, equipment damage, and fire hazards. Dimming lights is another consequence of voltage drop. In lighting circuits, voltage drop can cause lights to dim, especially at the end of long runs. This can create uncomfortable or unsafe lighting conditions. Sensitive electronic equipment malfunction as well. Electronic devices are often sensitive to voltage variations. Excessive voltage drop can cause these devices to malfunction, shut down, or experience data loss. To minimize voltage drop, several strategies can be employed. Firstly, increase the conductor size. Larger conductors have lower resistance and thus reduce voltage drop. Secondly, shorten the circuit length. Shorter circuits have less resistance and thus less voltage drop. Thirdly, reduce the load current. Lowering the current demand on the circuit reduces voltage drop. Fourthly, improve the power factor. Improving the power factor reduces the reactive component of the current, which in turn reduces voltage drop. The NEC provides guidelines and formulas for calculating voltage drop in electrical circuits. It recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. These limits are intended to ensure efficient and safe operation of electrical equipment. Ambient temperature refers to the temperature of the air or other medium surrounding electrical conductors or equipment. High ambient temperatures can significantly affect the performance and lifespan of electrical systems. When conductors are installed in high ambient temperature environments, their current carrying capacity or ampacity decreases. This is because the higher temperature reduces the conductor's ability to dissipate heat, leading to overheating and potential insulation damage. The NEC provides ampacity correction factors to compensate for high ambient temperatures. These factors are used to reduce the allowable ampacity of conductors based on the ambient temperature in which they are installed. It's crucial to apply these correction factors to ensure that conductors are not overloaded and that they operate within their safe temperature limits. High ambient temperatures can also affect the performance and lifespan of electrical equipment. Electronic components, such as capacitors and semiconductors, are particularly sensitive to temperature. Exposure to high temperatures can cause these components to degrade, leading to reduced performance, premature failure, and even catastrophic damage. To mitigate the effects of high ambient temperatures on electrical equipment, several strategies can be implemented. Firstly, provide adequate ventilation. Proper ventilation helps to remove heat from the equipment enclosure, reducing the ambient temperature around the component. Secondly, use cooling devices. Cooling devices, such as fans, heat sinks, and air conditioners, can be used to actively cool electrical equipment and maintain a safe operating temperature. Thirdly, select equipment with high temperature ratings. When choosing electrical equipment for high ambient temperature environments, select components and devices that are specifically designed to operate at higher temperatures. The NEC provides guidelines for directing conductors and equipment in high ambient temperature environments. It's essential to follow these guidelines to ensure that electrical systems operate safely and reliably. The overcurrent protection device, or OCPT, which is usually a circuit breaker or fuse, is designed to protect the electrical circuit from overcurrent conditions such as short circuits and overloads. Overcurrent occurs when the current flowing through a conductor exceeds its rated ampacity. Short circuits are low resistance connections between 2 points in a circuit that are supposed to be at different voltages. This results in a very high current flow, which can quickly damage equipment and cause fires. Overloads occur when the current flowing through a circuit exceeds its rated ampacity, but not to the same extent as a short circuit. Overloads can be caused by connecting too many loads to a circuit or by a malfunctioning appliance. The OCP protects the circuit by interrupting the current flow when an overcurrent condition occurs. Circuit breakers are resettable devices that trip open when an overcurrent is detected. Fuses are one-time devices that melt and open the circuit when an overcurrent occurs. The size of the OCP must be matched to the ampacity of the conductors it protects. If the OCP is too large, it will not protect the conductors from overcurrent damage. If the OCP is too small, it will trip unnecessarily, interrupting the circuit. The NEC provides tables and guidelines for selecting the appropriate size OCP for different conductor sizes and applications. These tables take into account the conductor's ampacity, the type of load it serves, and other factors. It's crucial to follow these guidelines to ensure that the electrical circuit is properly protected. In addition to protecting the circuit from overcurrent, the OCP also provides protection against ground faults. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as a metal enclosure or water pipe. This can create a shock hazard and can also damage equipment. Ground fault circuit interrupters, or GFCIs, are special types of OCPs that are designed to protect against ground faults. GFCIs detect even small amounts of current leakage to ground and quickly interrupt the circuit, preventing electric shock. They are commonly used in bathrooms, kitchens, and other wet locations where there is a higher risk of ground faults. Electrical metallic tubing, or EMT, is a type of rigid metal conduit commonly used to protect electrical wiring. It is made of galvanized steel or aluminum and is available in various sizes and thicknesses. EMT provides excellent protection against physical damage and corrosion. It is also relatively easy to install and can be bent to fit around obstacles. EMT is typically used in exposed locations such as walls, ceilings, and floors. It can also be used in concealed locations such as inside walls and above ceilings, but it must be properly supported and secured. When installing EMT, it's crucial to use the appropriate fittings and connectors. These fittings ensure a secure and watertight connection between the conduit and the electrical boxes or equipment. The NEC provides guidelines for installing EMT, including requirements for supporting, securing, and grounding the conduit. It's essential to follow these guidelines to ensure that the electrical system is safe and compliant. Non-metallic sheath cable, or NMB cable, is a type of electrical wiring commonly used in residential buildings. It consists of two or more insulated conductors enclosed in a non-metallic sheath. NMB cable is relatively inexpensive and easy to install. It is typically used in dry locations, such as inside walls and above ceilings. It is not suitable for use in wet or damp locations or in direct contact with the earth. When installing an NMB cable, it's crucial to follow the NEC guidelines for supporting, securing, and protecting the cable. The cable must be supported at intervals not exceeding 4 1/2 feet and must be secured within 12 inches of electrical boxes or fittings. The cable must also be protected from physical damage, such as from nails or screws. When running an NMB cable through holes in wood framing members, the holes must be drilled in the center of the framing member and must be large enough to allow the cable to pass freely without being pinched or damaged. It's also important to avoid running an NMB cable in areas where it could be exposed to excessive heat or moisture. A junction box is an enclosure used to house electrical connections. It provides a safe and convenient way to join wires together and to protect the connections from damage. Junction boxes are typically made of metal or plastic and are available in various sizes and shapes. They are used in both residential and commercial buildings. When installing a junction box, it's crucial to follow the NEC guidelines for selecting the appropriate size and type of box for the application. The box must be large enough to accommodate all of the wires and connections, and it must be suitable for the environment in which it will be installed. Junction boxes must be securely mounted to a structural member, such as a wall stud or ceiling joist. The wires inside the junction box must be properly connected and insulated, and the box must be covered with a blank cover plate. It's important to avoid overloading junction boxes with too many wires or connections. This can create a fire hazard. When making connections inside a junction box, it's essential to use the appropriate wire connectors. These connectors ensure a secure and reliable connection between the wires. The NEC provides guidelines for selecting and installing wire connectors. A thermostat is a device used to regulate temperature. It is commonly used to control heating and cooling systems in buildings. Thermostats are available in various types, including mechanical thermostats, electronic thermostats, and programmable thermostats. Mechanical thermostats use a bimetallic strip or gas-filled bellows to sense temperature changes. Electronic thermostats use a thermistor or other electronic sensor to measure temperature. Programmable thermostats allow you to set different temperatures for different times of the day, which can help to save energy. When installing a thermostat, it's crucial to follow the manufacturer's instructions. The thermostat should be mounted on an interior wall away from direct sunlight and drafts. The thermostat should also be located in an area that is representative of the average temperature in the room. When connecting the thermostat to the heating or cooling system, it's important to use the correct wiring diagram. The wiring diagram will show you how to connect the thermostat to the system's control panel. It's also important to ensure that the thermostat is compatible with the heating or cooling system. Some thermostats are only compatible with certain types of systems. The wire gauge in the electrical panel must correspond to the breaker size to ensure the circuit is protected from overcurrent conditions.